Hi calculus students, in this next video we're going to learn about the mean value theorem for integrals. If the mean value theorem sounds familiar, it's because we've learned about the mean value theorem before, but we learned about the mean value theorem for derivatives. And so just in case you want this, you don't necessarily have to write this down, but if you forgot what the mean value theorem for derivatives is, it's right here. So the mean value theorem for derivatives is when the instantaneous slope is equal to the average rate of change. And so the mean value says that if we have a continuous and differentiable function, then there exists some point C for which the instantaneous rate of change equals the average rate of change. And you can always figure out what that value is by setting the two equal to each other. And so we can observe that in Desmos right here. So we have the function, this is a cubic function. This cubic function is continuous and differentiable. And so there are many values where the instantaneous rate of change, which is this red graph, or the red line, is equal to the average rate of change. So here I just have the average rate of change between these two points, whatever that is. And I tried to make the red line as close as possible. But there, I could change this, so I changed the average rate of change like that, and then I could attempt to make the red line the same or parallel, so the slopes of them are equal to each other. Right here in Desmos is an image of what the mean value theorem for integrals looks like. So essentially, you can see this equation right here. It means that there is a line that occurs, so on a continuous closed interval, there is a value m for which the average value of the function of the integral is equal to m. Okay, so right now this picture might not be meaning too much for you, but hopefully once we go through some examples, you can kind of see what is happening here. All right, so here's the official definition. So f is a continuous on the closed interval from a to b. Then there exists a value c on the closed interval such that this is true. So the integral from a to b, the integral is equal to f of c times b minus a. So what this looks like graphically, I think it helps to draw a picture, is this. So if I have f of x, some sort of function, and I'm evaluating the integral from a to b. And so the integral would be representative of the area under the curve very precisely. There is also some value c, where I don't know where it would be in this case. Let's just put it right here. There's some value c for which we can form a rectangle from a to b that is equal to the green area. So the area of the rectangle, which is f of c times b minus a, is equal to this green area right there. So those two become equal. Hopefully my color coding semi helps. Maybe I'll show that that's a rectangle. Just like this rectangle over here. I bet your pictures look great. So this is like visually, this equation is helpful to think of this visually. Usually the way that the equation will be presented to you on the AP exam will be like this. So you can see they they divided by b minus a on the left hand side to get f of c by itself, and then usually we'll see it in this form. Okay, so there's a value f of c for which the integral, when we divide by b minus a, we're actually finding the average. So if we think of finding the total, this gives you the total, and then dividing by b minus a is dividing by that value of n, it's finding the average of the total. Okay, so when we think of mean, we should think of the word average. And so average is taking the total and then dividing by the number of objects. So in this case, we have b minus a. Okay, and so visually this looks more like that graph that I showed you on Desmos, where C, here's our f of C, this is our C value. There's an f of C that's equal to the average value. Okay, so let's look at this in the real, in a context. And we're actually going to skip to example 13 because I think that this shows a more straightforward example of how to apply this. And then we'll do 12 afterwards. So in 13, we're just trying to find the value of C guaranteed by the mean value theorem for integrals for this function right here. And then interpret the results graphically. Okay. So I'm just going to straight up use that equation that I see above. So I know there's a f of C for which this is true. 1 over b minus a. Here I have b minus a of the integral from a to b of f of x. Okay, and now we can figure out what is that value by solving the integral. So this is going to become 1 over 3. The antiderivative of 1 plus x squared is x plus 1/3 x cubed, and we're evaluating from -1 to 2, just using the FTC part 1. And then this equals 1/3. Plug in 2, I get 2 plus 8/3 minus, plug in -1, I get -1 plus -1/3. If I distribute the negative sign, we can make these all positive to simplify that a little bit. I'll keep my 1/3 on the outside and figure out what's in here. I'll combine 2 and 1 to get 3, and then 8/3 plus 1/3 is 9/3, which I can simplify to 3. So I have 1/3, 3 plus 3 is 6, so this equals 2. Whew. So I know that there's an value for which f of c equals 2. So this is what I found. There's an f of c that equals 2. And now I just need to figure out what is that c value. And so f of c, I'm going to go back to my original function. I'm just going to use my f of x and solve for c. So f of c is 1 plus, oops, not x squared, 1 plus c squared equals 2. And solve for c, c squared equals 1. And then take the square root, c equals 1. Am I right? No, I'm not right. Plus or minus? I hope you didn't forget your plus or minus. So the c value that is guaranteed is plus or minus 1. Okay, and we can think about what this looks like graphically. I'm actually going to go back to the Desmos. I'm going to type that equation in for my function. So the function is 1 plus x squared. Right there. And then I need to change the interval from -1 to 2. -1 to 2. There. And that's what it looks like. So from -1 to 2, the average value is 2. So you can see our m value came out as 2. Right here is our m value. It's 2. Oh, I'm changing it by accident. Oops. Didn't mean to move it. My bad. So m value is 2, and the places where that m value occurs, you can see on the graph, are at -1 and 1. So graphically, this is how you will interpret the results graphically. So I want you to pause this and add this graph to your solution, because in the problem you're asked to interpret the results graphically. Okay, so when you do this, make sure to show that the m value, or the height, your f of c is 2, And this occurs at the c values, x equals -1 and 1. Right there and there. Cool. Once you've got that, let's proceed. So 14 says to show that the average rate of change of a car's position. So let's kind of remember what equations we use. So the position function, remember, is going to be s of t, is the same as the average value of its velocity over the same function. So its velocity is going to be v of t. Just a reminder. So the average rate of change of a car's function. Average rate of change is f of b minus f of a over b minus a. And I'm going to plug in these values. So for finding the average rate of change in position, we use position function. So average rate of change of position, we'll use s of t2 minus s of t1 divided by t2 minus t1. This is the only information that we're given, so we're just going to use it in the general form. So here is what I got for that. Okay. The next thing we're going to solve out is we're going to need to show that it's the same as the average value of its velocity function on the same interval. So the average value of its velocity function, this problem is really emphasizing that there's a difference between average rate of change and average value. So average rate of change, you're always going to use this equation. And then whenever we see the word average value, we're going to use this equation that we just learned. So average value, we're using this. Average rate of change, we use the old one that we learned. Okay, so that's really the focus of this problem, is having you recognize that even though we have two things called average value and average rate of change are different. Okay, so using the equation above, we'll do 1 over t2 minus t1, the integral from t1 to t2 of the velocity. That's what we're finding the average value of. Okay. So this is 1 over t2, that's not t squared, t2. T sub 2 minus t sub 1. Applying the FTC part 1 to this, the antiderivative of velocity is position. So we're solving position function from t1 to t2. And then we can expand this. So this is s of t2 minus s of t1. And then combine these two things together, we get s of t2 minus s of t1 over t2 minus t1. And look, they're the same. So the average rate of change in position, we're basically proving that the rate of change in position is velocity. So the average rate of change in position is the same thing as the average velocity. Cool. So just to finish off my color coding, that is the answer to that. And they're the same. So this is a real life example. So it says in New Braunfels, which is a city in Texas, in New Braunfels, the temperature in degrees Fahrenheit, T hours after 9 a.m. is modeled by this function. So they're giving us big T to model the change in temperature. And it wants us to find the average temperature during the 12-hour period from 9 a.m. to 9 p.m. So I'm going to make a little note. Since we're starting at 9 a.m., this is T equals 0, because that was our start time. And then 9 p.m. will be T equals 12. Okay, so first finding the average temperature during that 12-hour period. So the average temp, we're using this equation up here. Remember, finding the average value. And I'm going to add this up here. This is average value. So whenever you see the words average value, this is the equation you use. Okay. So the average value will equal 1 over b minus a times the integral from a to b of our equation. So 50 plus 14 sine of pi t over 12 dt. Okay, no, we are not going to evaluate this by hand. This would be a calculator-enabled problem, so if we had a calculator, we'd just type this beautiful thing into a calculator, and we would get 50 plus 28 over pi, which is approximately 58.927 degrees Fahrenheit. Okay, there's my average value. This is A. Being able to set up the integral is really important. Sometimes in the free response questions, that's all you have to do is show what the integral is. So a lot of time with these problems, mainly they just want you to be able to set up the integral. So having this equation memorized for average value is very important. And then part B, find the values of T at which the mean value theorem guarantees the temp in New Brunswick was the average temperature. So right here, we need to evaluate the temperature. So we actually need to find the F of C, the C value for which this is true. So in this case, we're finding where T of C is equal to 58.927. So again, we're not going to solve this out by hand. We could do this on our calculators. And if you're not sure how to do this on the calculator, talk to me sometime in class. But we would take this equation, set it equal here. Since we have the fancy TI Inspires, we would literally just tell the calculator to solve this equation. And we'd get T equals 2.639 and T equals 9.3698. It would actually give us a lot of answers since this is a sinusoidal, and so there's infinite solutions, but we only need the ones between 0 and 12. And those two are it. Okay, so 12 is a really good application of the mean value theorem for integrals, but all of these, you should understand how to set up the integrals to find the average value.